Why are activation functions essential for neural network backpropagation? Have you ever wondered why activation functions are so important in neural networks? Let's break it down in a way that makes it easy to understand. Activation functions play a key role in how neural networks learn from data. They introduce nonlinearity into the model, which is essential for recognizing complex patterns. Without these functions, no matter how many layers a neural network has, it would only perform simple linear transformations. This limitation would prevent it from tackling tasks like image recognition or natural language processing. Now let's look at how this works. Neural networks consist of layers of neurons. Each neuron takes inputs, applies a weighted sum, and adds a bias. This sum is then transformed into an output signal by the activation function. This transformation is what breaks the linearity. If we only used linear functions, the entire network would behave like a single linear function, which is not helpful for complex problems. During the training process, neural networks use a method called backpropagation to adjust the weights and biases based on the errors in predictions. Backpropagation calculates gradients, which are the rates of change of the error concerning each weight. Activation functions are differentiable, meaning they provide these gradients. This allows the gradients to flow backward through the network, guiding how each weight should be updated to reduce errors. Let's consider a popular activation function, the Rectified Linear Unit. This function outputs 0 for any negative input and passes positive inputs unchanged. Its gradient is either 0 or 1. This property helps maintain strong gradient signals during backpropagation. It also prevents issues like the vanishing gradient problem, which can occur with older functions such as sigmoid or hyperbolic tangent. This characteristic allows for faster and more stable training of deep networks. In summary, activation functions are essential for three main reasons. First, they introduce nonlinearity, enabling neural networks to learn complex patterns. Second, they provide the necessary gradients for backpropagation to effectively update network parameters. Lastly, they help avoid problems like vanishing gradients, making it easier to train deeper networks. Understanding these functions is fundamental for anyone interested in artificial intelligence and machine learning. They are a key component in developing technologies that generate text, images, and other creative outputs. So, next time you think about neural networks, remember how vital activation functions are in making them work effectively.